towards the end of this problem set, there are several problems where we're just trying to make sure that you are reading the information correctly in terms of derivative and matching those things up with shape. So you don't have to find the sign chart. You can just think about what everything means. So for example, here's a statement involving the derivative. F prime of x greater than 0 means slope is positive. So they're telling me the slope is positive from minus infinity to minus 5, and then from 5 to infinity. So this graph, for example, looks like it probably has that going on. You can zoom in on it if you want to, but notice that the slope here is positive, so coming up to negative 5, and then also starting at starting at positive 5 and going forward, we're positive, and the graph is falling in between, and that's what this will tell us. The graph is falling in between. So this graph has the right basic shape. We should check everything else. Does it do these things? This is a list of places where the graph should have horizontal tangent lines because this is saying slope is 0, slope is 0. So is the slope 0 at negative 5? Yep. Is the slope 0 at x equals 0? Yep. And is the slope 0 at positive 5? Yep. So we can figure out that this is the only one that is behaving like this, like the description going on here. If these kind of things in the tables bother you, an easy in-between step is to take this table and transfer, not all the information will transfer, but transfer everything that does transfer over to a sign chart. Just give yourself the sign chart that we're used to seeing, and we can label it by saying we have pluses here, we have 0 here, minus 0, minus 0 plus. All of that information comes out of these facts, and then it's easy to work from the sign chart to that picture. I also wanted to show you one example where the derivative rule is a little more complicated than just a polynomial. So here's a problem. All the steps are exactly the same, but our actual original derivative calculation uses the quotient rule. So let's do that. So the derivative of this function is the denominator times the derivative of the numerator. And again, I'm not going to do it. I'm just going to write down that that's what needs to be done, minus the numerator times the derivative of the denominator, and it's all over the denominator squared. So now if I go back and do my derivatives, in the first term I have x minus 6 times 2x, and in the second term we have x squared times 1. Derivative of x minus 6 is just 1, and we do have that x minus 6 squared in the denominator. So I need to simplify my numerator, which I can do by multiplying the terms out. So x minus 6 times 2x will give me 2x squared minus 12x. I'm multiplying each term in parentheses here times 2x. And then here I have minus x squared times 1, which obviously is just minus x squared, and that's divided by x minus 6 squared. So we're almost done. In the numerator, there are some terms that combine. The 2x squared minus x squared is just x squared, positive x squared, and then minus 12x, same denominator. And then finally, I'll write that in a factored form. I have x times x minus 12 in the numerator, and x minus 6 squared in the denominator. I now move on to draw my sign chart. And we found that to make a sign chart, we first needed to know what our critical values were, and we find those by finding where the derivative is equal to 0 or undefined. Remember that when we have a fraction, for a fraction to be 0, for this fraction to be equal to 0, we have to have the numerator equal to 0. And for a fraction to be undefined, that happens when the denominator is 0. So when we have an answer for a derivative that's a fraction, all I need to do to find my critical values is to find where the numerator is equal to 0. And you can see that x times x minus 12 is 0 when x is 0 or x is 12. So that gives me two values where the derivative is 0. For my sign chart. And the denominator is 0. X minus 6 squared is 0 when x is 6. So the derivative is not defined. I have to write my zeros on here. Not defined at x equals 6. Now there is a technicality with x equals 6 because x equals 6 is not in the domain of f. In other words, x couldn't be 6 in the original function. This function is not defined when x is 6 because the function has a 0 in the denominator when x equals 6. So, so some books put a sort of a little dashed vertical line here. We still want it to be on our sign chart, but it is impossible at x equals 6 that x equals 6 could be a high point or a low point on our graph because there is no graph at x equals 6. So it should be part of the sign chart, but it's not technically what we call a critical value for f. So I need my signs. So I will pick some points to sample. So maybe 1 in here, maybe 7, 13, and -1. So I just have to have some points that I can sample and put back into my f prime formula. And it's always easiest to use this factored form if you have it. So this is my f prime of x formula, and so that's the easiest one to use. I can just put each of these values of x in, so f prime of -1. Again, I don't care whether I know the number or not, I just want to know whether it's positive or negative, so I can kind of play this game. If you put -1 in for x here, you'll have -1 times -13. That's positive. And in the denominator, you'll have -7 squared, which is also positive. So f prime of -1 is definitely a positive value. Similarly, f prime of 1 will be a negative value. By the same idea, 1 times -11 is negative, and the denominator will be positive. F prime of 7 is going to be 7 times -5, which is negative, and the denominator will be positive, so that'll be a negative value. And then finally, f prime of 13 will give me a positive times a positive in the numerator, so that's a plus. So I should have minus, 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 plus, plus, plus. And so this is what my sign chart looks like. Remember, I do not have a graph here, so that's not going to technically be a critical value, but it is something that's worth having on the sign chart. This graph is going to be decreasing. That's what it asks about. So our f is decreasing on the interval 0 to 6, and then also 6 to 12. So it decreases until it gets to this part where the graph's undefined, and then it decreases on the other side of it as well, all the way to 12. So that would be the answer to where's f of x decreasing. Local extreme values, well, here's a place where the graph must change from a positive slope to a negative slope. So the graph has a local max at that value, and then similarly the f has a local min at this value, because here we're saying the slope of the graph changes from negative to positive. That means the graph stopped going down, the graph of f stopped going down and started going back up at x equals 12. So we can get a lot of information even without drawing a graph about where this graph, the graph of f, has high points and low points.